Let y be a geometrical random variable with a parameter p, where p is equal to lambda times data. Define x is equal to y times the data, where lambda and data is greater than 0. Prove that for any x is greater than 0, we have the limit of the distribution function of x when data tends to 0 is equal to 1 minus e to the negative lambda x. Let's first compute the distribution function of y. So the probability y is less than or equal to n, where n is a positive integer, is equal to the summation k from 1 to n p times q to the power of k minus 1, where q is defined as 1 minus p. So this is just a definition of a geometrical random variable. So this is equal to p times 1 plus q plus all the way to q to the n minus 1. And this is equal to p times 1 minus q to the n, power of n, divided by 1 minus q. Now because p is equal to 1 minus q, so this can be cancelled. So this is equal to 1 minus p to the power of n, because q is defined as q is equal to 1 minus p. Now this is for a positive integer n. So for any y is greater than 0, which is not necessarily an integer, let's first introduce the notation floor. So this is defined as the maximum of integer that's less than or equal to y. For example, 3.2 floor is going to be equal to 3. Now let's compute the probability y is less than or equal to lowercase y. And this is equal to the probability y is less than or equal to the floor of y. This is because y can only take integer values, right? So for example, when we say y is less than or equal to 3.2, this is equivalent to say y is less than or equal to 3, because y can only take integer values. Okay. Delete this. So this is equal to, again, based on what we calculated here, so this is equal to 1 minus p to the power of y floor. Now we can calculate the distribution of x now. The probability x is less than or equal to x is equal to the probability, and recall that x is defined here. So this is equal to the probability y times data less than or equal to x, and this is equal to the probability y is less than or equal to x divided by data. This is because data is greater than 0. So this is equal to, based on the formula we just have here, so this is equal to 1 minus p to the power of x divided by data floor. Now let's compute the limits of this item. So this is equal to, let's compute and recall p is equal to lambda times data. So this right is lambda times data to the power of x divided by data. Let's first compute the limits of this piece, which is this item. Now let's write this as follows. So this is equal to 1 minus data, lambda data. In an exponential, we're going to write this as negative 1 over lambda times data. And we're going to multiply this negative lambda data. So this two is, if you multiply these two items, it's just 1. So times x over data floor. So we're going to write this as 1 minus lambda data to the power of negative 1 over lambda data. We're going to write this whole piece together to the exponential negative lambda data x divided by data floor. Now recall that recall this limit 1 plus t to the power of 1 over t. This converges to e when t converges to 0, right? This is just a fact. Let's recall this fact. So now if we treat this item as t, right? So when data tends to 0, this whole thing t tends to 0. So this whole piece inside this bracket is going to converge to e, right? So now to compute the limits of the entire item, so we just need to compute the limit of this piece. Okay. Next we're going to compute the limit of this piece. So now first let's look at lambda data x divided by data floor. Now this is less than or equal to lambda data x over data. This is because the definition, just because of the definition of the floor, and this is greater than or equal to lambda data x divided by data minus 1. Again, this is obvious based on the definition of the power of the floor. Now let's figure out what there's two sides. So this the right hand side is just lambda x, right? So this is just lambda x. Now when data tends to 0, what happens to this item? So let's write this as lambda x minus lambda data, right? So what happens when data tends to 0? So this item is going to tend to lambda x, and this side is also lambda x. So both sides would converge to lambda x. Since this is in the middle, so this must converge to lambda x as well. So now we just proved that this item, so here, which is this item, we just proved that this converges to lambda x, right? Now let's look at the entire thing. So this piece tends to e, and this piece tends to lambda x. So now this entire item here, that's right here, is gonna converge to. This is gonna converge to e to the negative lambda x, right? So or this whole thing is going to converge to e to negative lambda x, and this is just this item here. It's just this entire thing, right? So we have this entire thing is going to converge to 1 minus e to the negative lambda x, and this is what we want. Thank you for watching.